In this video, we're going to talk about the one-dimensional solution for multi-phase flow in porous media, where one phase is displacing another phase, and we're going to introduce the concept of fractional flow. So let's start with the equation that we're going to solve. This is the porosity. This is the saturation of one phase, say water, in the porous medium, where we may have another phase present, such as carbon dioxide or hydrogen or air or oil. And then we have a flow of that phase that's described by Darcys law. Okay, so this is my equation, and I want to set up essentially the equations to solve it in one dimension. Now it turns out that this isn't that straightforward, because unlike heat transport, I don't obviously have a saturation term here. So what I'm going to do is to go through a few lines of what appear to be rather tedious algebra before I can get to something that I can solve. But for completeness, we have to do it. So we derived this equation in a previous video. I hope that you can see that it doesn't require a re-derivation to have exactly the same equation for the second fluid phase that's in the porous medium. So this we can write like this. And then what we do is we sum those two equations, okay? Now, if we sum those two equations, we see we're going to have S1 plus S2, the saturation of phase 1 plus the saturation of phase 2. Now, if we assume that they're the only two fluid phases in the porous medium, then they completely saturate the pore space, so this is equal to 1. And the time derivative of 1, I hope your mathematics is good enough to see this, 1 is a number, it doesn't change with time, and so if I add them, this term becomes 0. So what I end up with is that dq1 plus dq2 by dx equals 0. And what I'm going to define is what's called a total velocity. Now, it's not a velocity. It is, in fact, the total volume of the two phases flowing per unit area per unit time is the sum of the two q's. So my total velocity is, so this is dqt by dx. My total velocity doesn't vary in space, so it's a function of time only. Now, why is that the case? We've assumed incompressible flow in one direction. So imagine I'm injecting water here, okay, and what's being produced here is gas, say carbon dioxide. If I inject a cubic meter here, and I've just got one-dimensional flow and the fluids are incompressible, then a cubic meter of gas has to be coming out the other end. If imagine I'm in the middle of the reservoir, but it's still one-dimensional flow, and I've got, say, half a cubic meter of water flowing in my unit time, then I need to have half a cubic meter of gas. So anywhere in one dimension, the volume that I inject has to be the same volume flowing everywhere, even though what phase it is can change. Okay, so we inject one phase and we normally produce the other, and in the middle of the reservoir we have both phases flowing, but the total velocity is a function of time only. I can pump harder or less hard, but in space it doesn't change. The other thing that's important when we're doing this is a boundary condition. As an engineer, you choose what QT is, right? You decide how rapidly you're injecting one phase. You want to do CO2 storage, you design the CO2 storage to inject the carbon dioxide at the rate you want, okay? So QT is not some mystery object, it is a boundary condition. It's a boundary condition basically set by the engineer. If we're doing a laboratory experiment, again, it's the rate at which you're injecting through the pumps. Okay, so that's the first step. Now, the second step is we need to invoke Darcys law. Okay, so we're going to write Darcys law as follows. This is phase 1, and we're going to write it in this form. lambda here, it's a Greek L, is a mobility, and it's going to be the relative permeability divided by the viscosity. Okay, so the reason why in the multi-phase Darcy law we always have a relative permeability divided by viscosity, and it gets a bit tedious to keep writing it every single time, and we're bound to make mistakes. So I'm going to define a mobility, which is the relative permeability divided by the viscosity. This is a function of saturation. Okay, so the multi-phase Darcy law says the volume of phase 1 flowing per unit area per unit time is the absolute permeability times this mobility, and then we have a pressure gradient and we have the gravitational term. Okay, and we can write the same for the second phase. And I seem to be running a little bit into the other equation here, but don't worry about it. Okay, it's the same functional form. Okay, so I've written that because now what I'm going to do is I'm going to sum them, and I'm going to find my QT, because QT is a boundary condition, so I have a bit of control over QT. Okay, so I'm going to write QT here, and I'm going to write my equations here, but there's one thing that's still missing, is I've got a P1 here and a P2 here. So I've got two pressures. That's a little bit awkward. So I want to get rid of those two pressures, and I do that using capillary pressure. Right, so that we also know, and I write it down the bottom here, is that P2 minus P1, if you remember my previous videos, that's defined as the capillary pressure. And that is also traditionally written as a function of saturation. So instead of P2, I'm going to write PC plus P1. Okay, so now we got everything we need. So let's look at this carefully. We got a K lambda 1 dP1 by dx plus and a minus K lambda 2 dP1 by dx, right? And I'm going to write that as K lambda T. I'll be quite explicit what I mean by that in a moment. Okay, lambda T is the total mobility. So lambda T is, write it here, is the total mobility. Bit like the total velocity, it's the sum of the two lambdas, right? So we go lambda 1 plus lambda 2. Okay, so that's that term. There's the PC term, right? Let's not leave it out. So when we add these two, we've got a minus K lambda 2 dPc by dx, okay? Because we've got the PC and then a derivative. Okay, now we've got some gravity terms, and those are going to be positive. Plus K lambda 1, lambda 1, K lambda 1, rho 1 gx, and then plus K lambda 2, rho 2 gx. Okay, so there we have the total velocity. Now, this is a bit of a mouthful in terms of the equation. What it actually means physically is this is fixed, and if I knew, just imagine I've solved the equations, don't worry, we will. So I know the saturation everywhere, and I know these functions, these complex functions of saturation, the lambdas and the capillary pressures, then I'd actually know all of these terms. So what this can be done is that it can be used to find the one unknown, which is my pressure. So if I know QT and I know all these other functions, so if I know PC and I know the saturation as a function of distance, I can actually find the pressure. I can derive the pressure. Basically, I can integrate this equation with a bit of rearrangement. I'm not going to write down lots of algebra to do it. It doesn't get you anywhere. It enables you to find the pressures. What I'm going to do instead is I'm just going to eliminate pressure from the equations and end up with an equation which is sort of where we thought we were starting, an equation that just has saturation in it. So in Darcy's law, pressure pops up, okay, and now we've got to solve for saturation and pressure, but I'm going to get rid of pressure. So I'm actually going to eliminate this term from the equations. And how I'm going to do it is I'm going to write this is equal to this, and then I'm going to add this, and I'm going to minus this. So I'm going to put all of these terms, okay, over this side of the equation, okay, like that. Right, so that's what I'm going to do. So now I'm going to write Q1, and I'm not going to write dP1 by dx. I'm going to write it in terms of Qt. So let's see how this goes. So Q1 is equal to minus k lambda 1 dP1 by dx. Well, here we've got minus k lambda t dP1 by dx. So this is going to be lambda 1 over lambda t, divide through by lambda t multiplied by lambda 1. The minus I'm going to keep. So what's on this side of the equation? There's just a qt. Okay, here. Now remember, we put this term over here, and there's a lambda 1 over lambda t. So this is another positive term, k lambda 1 over lambda t. That's basically this bit and this bit. And then there's a lambda 2 dpc by dx. Now we need to think about the gravity terms, because we've got a gravity term here and we've got these gravity terms. So let's do these gravity terms first. These are all both a negative. If you notice they're minus. Okay, so it's a minus k. There's a lambda 1 and there's also a lambda 1 here. So it's lambda 1 squared. Oh dear. Right, that's going to be rho 1 gx. Okay, there's going to be this one, minus k lambda 1 lambda 2 rho 2 gx. And there's a lambda t as well. And then we've still got this term, right? We sort of left this one out. That's the dp dx got rid of. And then there's a plus, and I put it here, plus k lambda 1 plus k lambda 1 rho 1 gx. And I don't need to divide by anything because that's just Q1, right? So that's fine, and I've deliberately left a gap there. Don't worry, that isn't a mistake. Now, at this point, it's all a bit, looks a bit obscure, but I just want to deal with the gravity terms because they seem to be all over the place. Okay, so this term I'm going to have a physical explanation for, this one, but what's going on here with all this gravity? So what I'm going to do is I'm going to put this term divided by lambda t, and then lambda t is, where was it? Lambda 1 plus lambda 2. So I'm going to put in here lambda 1 plus lambda 2. Okay, a bit small, but I can do it. Okay, and the reason why I do this is that, of course, some terms are going to cancel. Okay, I've got a minus lambda 1 squared rho 1 g1 of lambda t and a plus lambda 1. So this term cancels out with this first term here. Okay, and now I've got k lambda 1 rho 1 gx over lambda t minus k lambda 1 lambda 2 rho 1 gx minus k lambda 1 lambda 2 rho 2 gx. So I'm going to write these two gravity terms. Okay, I can write this as k lambda 1 lambda 2 delta rho gx over lambda t, and delta rho is just the density difference, and it's the density of phase 1, and that's normally water. That's typically, and by convention, the denser phase, and phase 2, which is CO2 or hydrogen or oil or natural gas, is the less dense phase. So this is normally a positive number, and that's the density difference. So now we've written Q1, okay, in terms of either saturation dependent terms or our imposed boundary condition Qt. And we'll then go on to show how we can then construct solutions. So let's write out the water Darcy flux again, and I'm going to rearrange the terms slightly. So this is the volume of phase 1 that flows per unit area per unit time. And there are 3 terms, and these 3 terms have physical meaning, so we're going to talk about those. Lambda 1 over lambda t times my total velocity. The second term, traditionally actually you write the gravitational term next. So this was permeability. There were the product of the mobilities divided by the total mobility, and then there was a delta rho gx. And then there was a final term that was capillary pressure, and that again had a k lambda 1, lambda 2 over lambda t, and then there was a dpc by dx. But capillary pressure, as I said, is a function of saturation. So let's write this instead as dpc by ds1, and then we have a spatial derivative with respect to x. So now let's just think about those, because yeah, it seems like a sort of bewildering bunch of terms, but let's talk about them physically. This first term is advection. It's going with the flow. So how much water is flowing? Well, we impose a total velocity. Okay, say we're injecting water, so near the injection well, we're just injecting water. The mobility of water is the same as the total mobility because the oil has been, or the CO2 or whatever phase we're displacing has been reduced down to essentially a residual saturation where it doesn't flow. So this is 1. So the flow of water is the total flow. Near the production well, for instance, maybe all that's coming out is gas. Okay, and there's no flow of water, so this is 0. If we're in the middle of the field and we have both phases flowing, say gas and water both flowing, then the water flow, say Q1, is simply driven by the ratio of mobilities. And that should be sort of intuitive. It's like current flow, and you've got two resistances, right? Which one, you know, how much current does each one? It's the ratio of the inverse of the resistance, right? So it's the conductance of each of the wires, okay? So it's the same. It's basically, this is a flow conductance, okay? And it's the ratio of those that tells me how much the water flows. But there are two other effects, okay? This one is gravity. So if I inject, again, I'll take water displacing gas as an example, or gas displacing water. So if water displaces a gas, it will tend to want to move downwards in the reservoir. If I'm injecting gas, say, storing carbon dioxide, that CO2 would want to rise. Okay. Now this is what's shown here. The flow is driven by a density difference. And this is one thing that often confuses people with Darcys law. They say, oh yeah, but in Darcys law, you've just got a rho g term. But actually, when you go through the equations, what governs the flow is obviously a density difference. That's physically correct, okay? So it's driven by a density difference, okay? If it's water and we're assuming flow downhill, that's water moving down. If it's carbon dioxide, it's water moving up. This is negative because it's moving uphill. Okay. Why the two mobilities? Because it's actually not just flow under gravity. It's gravitational segregation. It's the sense of, say, carbon dioxide going up and water going down. If you've just got carbon dioxide, it's just carbon dioxide flowing governed by the total velocity. It's only when there's both phases, the lighter phase, the less dense phase going up, and the more dense phase going down. So it's gravity segregation, and it's driven by both mobilities because both phases have to move. The final term, and we're going to show that's a diffusive term, is due to capillary pressure. Okay, it's exactly the same thing. It's driven, okay, by changes in capillary pressure. Okay, again, if we imagine, say, water imbibing under the force of capillary forces, okay, under capillary action, imbibing into the rock to displace, say, a gas, the gas has to move out. So again, it's driven by both mobilities. This term, by the way, it is a positive term. It has a positive magnitude. And the reason is, and this sort of obvious because it's all positive numbers, but if we think about how saturation might vary with X, if we were, say, injecting water, we start with a high saturation and it decreases. So ds dx is actually has a negative value, but if we think about what capillary pressure looks like as saturation, I'm just drawing little schematic curves. I'm not attempting to be super accurate here. Again, this derivative is always negative. So we actually have two. These actually both have negative values, okay, whatever they are, but multiplied together, that's a positive term. We can define now a fractional flow. And the fractional flow is just defined so that Q1 is some fractional flow, F1, of the total velocity. So the fractional flow is just this divided by the total velocity, so it cancels out here, and I put it down here. I'm not going to write it out, right? It's just an exercise in writing at this point. Okay. Turns out that we can solve the governing partial differential equation, which I will write out again just for really in two limits. So I want to talk a little bit about that, and then I'm going to say how we go about at least one of those limits. So if we go phi ds dt plus dq dx. Now, if you've been watching the other videos, now perhaps you can see where we're heading here. This part is just a saturation dependent form. This part is saturation dependent and also has a derivative. So let's look at how that sort of shapes up mathematically. Okay, I can write a fractional flow without capillary pressure, which ignores this capillary pressure term. And if I do that, then I don't have this second derivative. This is all just saturation dependence. This is just a function of saturation, complex nonlinear function, but just a function of saturation. This is a function of saturation with a saturation derivative as well. Okay, so if we look at this, we can write this as phi ds1 by dt plus, if we write here q1 is f1 qt, qt is not a function of x, right? We showed that dqt by dx is 0. So this can come out of the equation. Then we got df1 by dx, but df is just a function of saturation. And then we got, okay. And then we have the capillary pressure term. Okay, so F1N is no capillary pressure. And then we got a capillary pressure term. And I'm going to write it like this. And this D is basically what's left behind here. Okay, but I've kept in the ds dx and I've kept in the d by dx. So what is D? D is essentially a capillary diffusion or dispersion, and it's the terms that I haven't explicitly written down. And this is just a function of saturation. The only thing that's suddenly, there's a minus sign. Yes, there's a minus sign because I've taken it over this side of the equation. But D has a value that is either 0 or positive because dpc by ds has a negative value. Okay, so this is the form of the equations that we're going to look at. We have a time derivative here. Okay, we have a spatial derivative, but whereas in heat transport we could say this was a constant, this is now a function of saturation, so it's non-linear. And then here again we have a diffusive term, a second derivative, but again this isn't a constant, it's a non-linear function of saturation. So it turns out we can't solve this equation in general, but we can solve it in one of two limits. Either we ignore capillary pressure, and then we have a non-linear essential advection equation, or we ignore the advection and we have a non-linear diffusion equation. And those are the two limits that in subsequent videos we're going to go through. But let's just motivate that briefly, why we might want to do these two limits. Capillary pressure, if you've seen previous videos, normally has a magnitude of a few kilopascals. So you can see this is driven by a pressure here of the order of a few kilopascals. On the other hand, although this is not explicit, QT is driven by a pressure difference between wells. That pressure difference is normally megapascals or more. Okay, we're normally looking at tens, if not hundreds, of atmospheres pressure. Here we have a delta rho G, and really a pressure difference is a delta rho GH. Density difference is a few hundred kilograms per cubic meter times G, that's a few thousand, times H, which is of order in a reservoir, maybe tens of meters. So here we're not looking at kilopascals, we're looking at tens, maybe hundreds of kilopascals. So at the field scale, the explicit magnitude of this term is quite small. And so compared to the others, we can ignore it. And so in the subsequent videos, I'm going to go through an analytic solution where I ignore this term because its magnitude is small. I know this seems a bit obscure because it's lots of equations and we haven't gone through it in detail, but I can tell you in general its magnitude is small. There is, however, another limit where it's the other way around. And this we see in many manufactured devices. If I spill some water on my shirt, if we're looking at what are called gas diffusion layers in electrochemical devices, here we're not actually injecting fluids at all. One fluid is moving in and the other is moving out. QT is actually zero. There's no net flow. One thing's going in and one's going out. Gravity is relatively weak because we're looking at small distances. And in fact, the behavior is driven by this. Even if we're in the steep subsurface, if we have a fractured reservoir, the water, for instance, or the gas that we inject zooms along the fractures, but we have the matrix, the ordinary rock, and the only way in which fluids can go in is a fluid goes in and the other fluid comes out. And because we're looking at incompressible flow, our total velocity again is zero. If we're looking at a small system and gravity is weak, it turns out that this becomes the dominant term. So there are physical cases where either this is the dominant term or this is the dominant term. And that does make physical sense. They're not just mathematical conveniences. So in the subsequent videos, we're going to show how to solve this equation in these different limits.